All right, let's talk about the most famous equation in history. E equals mc². What if I told you it wasn't just some flash of genius, that it was actually unlocked by upgrading a tool physicists had been using for centuries? Well, today, we're going to see how adding just one single dimension to how we see the world revealed one of the deepest secrets of the universe. So, for hundreds of years, right, physics basically ran on Newton's rules. Space was like this giant, rigid box, and time was this universal metronome, just ticking away the same for everybody, everywhere. Simple. But then along comes Einstein, and he just shatters that entire picture. He tells us, nope, space and time are actually tangled up together in this four-dimensional fabric called space-time. And just like that, boom, all the old tools physicists were using to measure the universe, they were broken. See, in that old Newtonian world, we used these things called vectors. And really, they're just arrows. You draw an arrow to show which way something's going and how fast. And they were perfect. Why? Because they were drawn on a map of reality that we thought was totally static, totally unchanging. But here's the kicker. In Einstein's universe, that nice, neat map gets thrown out the window. Now, reality is this dynamic four-dimensional thing where space can literally stretch and time can slow down. So, how do you draw an arrow on a map that's constantly warping and squeezing depending on how fast you're moving? An arrow that means one thing to you standing still means something completely different to your friends zooming by in a rocket. So, physicists had a problem to solve. They needed a new kind of arrow, a better arrow, one that didn't just point through the three dimensions of space, but through space-time itself. The goal was to find a tool that would give the same answer for everyone, no matter how fast they were going. And this is that new tool. Enter the four-vector. And it's pretty much what it sounds like. It's an arrow, but it has four parts, four components. You've got your usual three for space, left, right, up, down, forward, back. But then you add that all-important fourth component, time. And here's what makes it so powerful. A four-vector doesn't just point from, say, your house to the grocery store. It points from one event to another. And an event is super specific. It's not just a place. It's a place at a certain time. So it's like an arrow pointing from my kitchen at 9 a.m. to the office at 9:30 a.m. Okay, so we've got our new upgraded tool. Let's take it for a spin. We can start by completely rethinking something as basic as motion itself. Using this four-dimensional thinking, we can now map a particle's entire history through spacetime. And this path has a really cool name, a world line. Seriously, think of it like the particle's full biography. Every single place it's ever been, at every single moment in time, all traced out as one continuous line. Right, so if the world line is the complete path, then we need a way to talk about how fast something is moving along that path at any given instant. And for that, we have the four velocity. It's not just your speed through space, it's your velocity through space-time itself. Yeah, the four velocity is kind of like a compass needle for your journey through space-time. Imagine that world line again. At any single point on that line, the four velocity arrow is perfectly tangent to it. It's just kissing the curve, showing you the exact direction you're heading through space-time at that precise moment. Okay, so we have a new way to describe motion. So what? Why does any of this matter? Well, this is where it gets really good. Because this new toolkit isn't just about fancier math. It's about uncovering deep, universal truths about reality, truths that were completely hidden from us before. Here's the thing. If you and I are moving at different speeds, we're going to disagree on stuff. We'll measure time differently. We'll measure distance differently. We'll even measure energy differently. But, and this is the magic of four vectors, they give us a way to combine all those things that we disagree on to find the things we always agree on. These unchanging quantities, these are the real laws of physics. And the most important of these universal things we can all agree on is something called the energy momentum four-vector. And just like its name says, it's a special four-vector that neatly bundles a particle's energy and its momentum together into one single object. Okay, I know this equation looks a bit scary, but stick with me. All it's really doing is calculating the length of that energy momentum four-vector. Think of it like a souped-up Pythagorean theorem, but for space-time. And here is the absolutely amazing part. It doesn't matter how fast you're moving when you do the measurement. It doesn't matter what you measure for energy or what you measure for momentum. When you plug it all into this recipe and calculate the length, you always get the exact same number. And what is that number? It's the particle's mass. So this tells us something incredible. A particle's mass isn't just some random number we tack on. It's a fundamental, unchangeable property of that particle. It's a truth that's literally woven into the geometry of space-time itself. I mean, you can't get more fundamental than that. And right here, hidden inside this one universal truth, is the big payoff. This one simple idea, that the length of the energy-momentum four-vector is always the mass, is the key that unlocks the most famous equation in all of science. So let's do a quick thought experiment. Let's take that big universal equation and look at the simplest possible situation. A particle that's just sitting there, not moving at all. Well, if it's not moving, its momentum is zero, right? So we plug zero into the equation for momentum, and poof, all the complicated bits just disappear. And what we're left with is something beautiful and incredibly simple. Yep, E equals mc². It just falls right out of the math. And you have to understand, this isn't just some formula you memorize for a test. It's a profound statement about what reality is. It says that mass isn't separate from energy. Mass is energy. A mind-boggling amount of concentrated energy locked up inside every bit of matter. And we found it just by following the logic of our new tool, the four-vector. So let's just recap the journey we took. We started in Newton's world of separate space and time. Then Einstein came along and fused them into space-time, which meant we needed a new tool, the four-vector. Using that tool, specifically the energy-momentum four-vector, we found a universal truth, an object's mass. And that one truth led us straight to E equals mc². It showed us that mass and energy are just two different faces of the same coin. The four-vector isn't just math, you see. It's the language that space-time speaks. Think about that for a second. Just by adding one more dimension to how we look at the universe, we uncovered the deep connection between matter and energy. It really makes you wonder, doesn't it? What other fundamental truths are hiding out there, just waiting for us to find the right perspective? What secrets are sitting just beyond our normal three-dimensional view of the world?